Ever wondered why iron glows red hot? Why fireworks make colourful explosions? Or why that thing you did in chemistry works? I'm here to tell you that they all work thanks to Emission Spectra! In the Bohr model, electrons in the pattern 2, 8, 8, 16, etc. orbit the nucleus. When an electron is given energy, it'll transition to a higher set energy level, and with enough energy, it'll become a photoelectron through ionization. In accordance with entropy, an excited electron will always want to transition to a lower energy state. In the demonstration being shown, the E represents the electron and the steps represent the orbits. When the electron is placed on top of the step, it will always want to find its way to the lowest energy state possible. During its transition, the electron will emit energy as photons and packets. Sometimes the lowest possible energy level is not n equals 1, but can be any energy level. An energy packet is called a quantum, and is equal to Planck's constant times the frequency of the photon emitted. Because more energy is required to make bigger jumps, the frequency of light emitted will be dependent on the magnitude of the transition. So when the electron travels a huge amount, UV radiation will be radiated. When traveling to the middle, visible light will be given off, and in smaller energy changes, infrared rays are given off. Each element has a different electron configuration. This means that the frequencies radiated will differ for each element. This table shows the Balmer series for hydrogen. Balmer series concerns only the transitions to the second orbital. N represents the principal quantum number, or the orbit number. The name of the transitions are named sequentially in Greek. H-alpha is the transition from n equals 3 to n equals 2. H-beta is from n equals 4 to n equals 2. The wavelengths in nanometers describe the photon being emitted. Visually, when hydrogen transitions from orbital 3 to 2, it will emit a photon we interpret as red. From 4 to 2, aqua will be emitted, then violet, then UV. The wavelengths of absorption and emission spectra can be found through using Balmer's equation. In this equation, lambda is the wavelength, B is Balmer's constant, and N is the principal quantum number. As displacement between the transitions increase, the wavelengths shorten, therefore frequencies increase. Because of the energy-frequency relation, the energy radiated will increase proportionally. The colours in the series increase in the same trend as the electromagnetic spectrum. Red has the lowest visible wavelength, while blue and violet are more energetic. Ultraviolet is invisible to the human eye and is more energetic than violet. In summary, an electron will jump orbits when energy is absorbed. Entropy will cause the electron to radiate its energy in the form of a photon. The frequency of the photon will depend on the amount of energy radiated. The electron, having lost its energy, will fall back down to the lowest possible energy state.